Greetings and welcome to a new video about analog filter design. In this example we will look at a very special filter, which is the delay filter. We will see how we can design this using the Bessel response characteristics. Of course we will see everything step by step in our calculations and verify these in SPICE simulations. Before we jump to our design example, let's first discuss the time delay operation. In general form we can say there is a function or a signal which is given by this waveform, just this red one, and it now operates a delay on it, and then the input voltage or input signal will be then delayed by this much. This is what we call a time delay. Now you see time delay as the basic operation in most signal processings, and we have also a specific time delay that can be created using electric circuits. So that is the realization of this time delay. And time delay can be also made linearly dependent on the signal frequency, which is very handy for, again, signal processing. And the mathematical expression, the time delay is, as said, is a time domain operation. So the units are in seconds, let's say 10 seconds or 10 microseconds. And the filters are usually designed using frequency domain specifications like the cutoff frequency, which is given in hertz or radians per second, the passband gain, and the phase is always in degrees or in radians. So we need to make a translation or the transfer from the time domain to the frequency domain and then getting back again to verify our design. So therefore we need to relate this time delay and the specific specifications in our filter. And the time domain representation of a signal, in this case the output voltage, can be given as a function of the input voltage as a delay here, which is given by minus d. So it is delayed by d seconds. That is in the time domain. But you can also do it in the frequency domain using the, first we of course transform that in the frequencies using the cosine expression where you see the amplitude, and the omega where you see the radians per second. And this is for the input as an expression. The output is then the delayed version where you replace this t for your input by t minus d, which is actually shown here. Now if you work it out, this output voltage expression, you can then have omega times t and omega times minus d, which is then minus omega d. And this is the addition compared to the input voltage expression. So the output and the input will differ only by a phase, which is then given by this minus omega d. And we define it here now as the theta. The phasor form, if you keep the frequencies exact same, can be also said like so. We can say the input voltage is the amplitude, phase, in this case 0 degrees, because there is no phase shift here. And the output is then again the same gain or same amplitude, because there is no operation in the gain here or the amplitude. And there's also some specific phase, which is in this case again the theta. And this theta is also minus omega d. So the transfer function, which is the output over the input, that is given by this t, is then written like so. And you see here that the a's will cancel, it is just 1, and you have now here directly the expression only as a difference in the phase. Now giving that in the diagram, in the plot form, you can see that this is now the omega, which is our radians per second, the frequency, and this is our phase. Now since this is minus omega d, this will be a linear decreasing line, which is slope of minus d. And the magnitude of this transfer function, which is the absolute value of the t, which is always 1, because that is the magnitude here. So these are the relationship between the mathematical expression of the delay and the frequency response here. Let's go to the design example and see this in more detail. What we want is a Bessel response delay filter design, and we will use the Sallen-Key filter circuit to realize this circuit. The specifications, we like to have a delay, so time delay of 100 microseconds, so this is given by this capital letter D. The maximum error in that delay must be 10% if you look at 4 kHz. In addition, maximum passband attenuation at 1.5 kHz must be 1 dB. Okay, how do we tackle this problem? Okay, let's see that in the first step. First we go to the normalized specifications. So from here we make it normalized. We use that to calculate that using the tables for the Bessel response. Now for multiplying the given values here by this time delay, which is then in this case 10 to the power minus 4 seconds, which is 100 microseconds, then you get your normalized specifications. Now that means we multiply this here, this 4 kilohertz, of course, times 2 pi times d, and that will then result in this 2.513 radians per second. Of course, everything must be translated in the radians and not in the hertz. That's why we first multiply this 4 kilohertz by 2 pi and then times d. That's the normalization operation for the time delay error. And also the passband attenuation must be normalized. So we go here again, 2 pi times this 1.5 kilohertz times again this d, and that will result in 0.9425 radians per second. Now those two values are already imported, so we need to use that in the table. Okay, step 2 is our filter order. Now for that we need to look at a table. So there's no specific formula for that, not like as for example in the Bode response or the Chebyshev response. You see here the table for the time delay error, so in percentage d at the normalized frequency. So we have already normalized this. You see here the errors, 1%, 10%, 20% and 50%. So we look at this column. You see also that the filter order is going up in this way. Now we see here the time delay error for 10% again occurs at this 1.94 radians per second as the normalized frequency, which will give us then a third order filter. Let's see from the table. But is it sufficient? Now, if the time delay will increase above 10%, that means if this frequency will increase, for example, goes to 2 radians per second, then the error will also increase above this 10%. That's the reasoning actually for this one. So this is actually what you can get at max in your normalized frequency. So that means NS3 isn't enough for this situation, looking only at the time delay error. If we go, of course, to 2.5 radians per second as we have it in our normalized value, that will make a problem. So if I look now further, now then you get here 2.84 radians per second as the normalized frequency. And that will do the job because that is lower, higher than this value. So that means the NS4 will do the job for this situation. It is sufficient for our time delay error. So that means we require a fourth order filter specifically for looking at the time delay error. Okay, the next one is about the attenuation, because there's also a specification of the passband attenuation at this frequency of 1 dB. Now again we see different columns, so 0.2 dB, 0.5 dB, 1 dB and 3 dB. So we look again at the specific dBs we want. Again our filter order goes up. Now we see here at 0.8 radians per second here, that will happen at the second order filter. Is this sufficient? Now if you use the second order filter, for example, just looking at the passband attenuation, now going beyond this 0.8 radians per second will make the attenuation larger than 1 dB. So that means, again, as said here, if we increase this 0.8 radians per second, you also go above this attenuation of 1 dB, which is not what we want, because this is the maximum allowed attenuation. So that means NS2 is not enough for this specific situation here, for our passband attenuation. Now, looking at again the table, we can go up and you see here 1.05 radians per second. That is again the normalized frequency, and that is larger than what we have here. So this is indeed sufficient. So if, for example, if you go here, you will not reach this value. That is actually the maximum value you can get here in your specifications. So this will do the job for the passband attenuation. But we have two specifications. We have the maximum time delay error and the maximum passband attenuation. Now for the first one we had NS4, and the other one will have NS3. So how do we then design this filter? Now of course, in order to meet both specifications, you need to of course have also a fourth order, because otherwise you will not meet these specifications here. So to meet both specifications, we require a Bessel response filter, which is a fourth order filter. Okay, that means we will get more attenuation than required here. That is because we take it one order higher. Okay, that's also what we see here. Okay, now let's go to the step 3, which is the circuit realization and the component values. We need to have a 4th order filter. That means you will use a Sallen-Key filter circuit, which requires 2 stages. The first stage will be a 2-pole Sallen-Key low-pass filter, and the second stage will be again a 2-pole Sallen-Key low-pass filter. In cascade, you'll get a 4th order filter. And this is the circuit for a 2-pole low-pass filter Sallen-Key configuration. Okay, getting the information here, and the table what we need now is about the natural frequency and the quality factor for each stage. You see also here the filter orders, natural frequency and the quality factor for the first stage, the second stage, third stage, fourth stage, etc. for the filter orders 1 up to 8. Now looking at our NS4, which is our 4th order, you see here the natural frequencies and the quality factors for each stage. That means here the stage 1 will require a natural frequency of 3.023 radians per second and a quality factor of 0.522. The next one is about 3.389 and 0.806. So the frequency scaling factor we need to now do is the KF, and for each stage that will be equal to the natural frequency omega n. So that's what we need to do. And also need to make the magnitude scaling factor, which is the Km, that is what we also need, and that is in this case taking as 10,000, so 10 to the power 4. That means all the resistors we have seen, our 2 R's in our Sallen-Key filter, will be 10 kilo ohm. This is an arbitrary choice. You can also make here 5 kilo ohms or 1 kilo ohm. That depends on what your preferences are, but this is of course also perfectly fine for other values. Now, using the specified time delay and the quality factor from this table and the magnitude scaling factor we just selected and the frequency scaling factor, of course again from the table, we can calculate now the capacitor values in the circuit. The circuit is shown here. You see here again the resistors, 4 resistors, each 10 kilo ohm, and we need to calculate the capacitors C1, C2, C3 and C4. So 4 capacitors we need to calculate using the magnitude scaling factor and the quality factor and the frequency scaling factor we have here. So for stage 1 we can calculate the C1 using this formula. You see here the Q1, which is the quality factor from the first stage, the D, which is our time delay, which is here 100 microseconds, and the magnitude scaling factor and the KF1, which is the frequency scaling factor for the first stage. That's all here, you see that. So you see here again the omega n1, just copy that here, 10 to the power 4, which is Km. Since Km is everywhere the same, so I haven't designated as Km1 or Km2, and the quality factor again from the table. Now, if you do that, you get here almost 2.45 nanofarads. C2 is calculated using this formula, again this time delay, D, and the quality factor, the magnitude scaling factor, and the frequency scaling factor. Again, do the math here, you get here almost 2.17 nanofarads. That's for stage 1. So this and that is now calculated. Stage 2 for the C3 and C4, that is calculated in the really similar form. Just replace the indexes here by 2. Now this will be then Q2, that will be then here from this table. And the KF2 will be then also from the table. And the Km is again 10,000, and you get here this 4.757 nanofarads. And C4 is similar to the C2 calculation, and that will result in 1.83 nanofarads. So we have the 4 capacitors for this circuit. Okay, let's now look at that Bode plot for the gain and the phase for our design and verify our calculations. Now let's start first with 1.5 kilohertz. Here you see there is a gain of minus 0.557 dB. Now it was allowed maximum 1 dB, so this is indeed as we wanted, so lower than maximum allowed, and that's perfect. You see also the phase here at 4 kilohertz, which is minus 142.96 degrees. This specification we need to look at in more detail to verify the time delay in that circuit also, so we will see that shortly. This is also the circuit we have designed. You see also the component values C1, C2, C3 and the C4. Okay, so this is indeed as we wanted for our passband attenuation specifications. Okay, looking now at the simulation result also for the Bode plot. First we start with the phase to set the reference point. I will clarify this in more detail in this plot. You see now here the plot only for phase, so in degrees. And this here is the frequency, again log scale from 1 micro, 10 micro, 100 micro, 1 milli and 10 millihertz. You see here already a label, so I will clarify this here in detail. We like to first designate or find a reference time delay for our calculations for the maximum time delay error. Now the error we want is determined as the percentage error in a time delay referred to the time at DC. That is officially what the definition is, so it is at 0 Hertz. But the definition uses now DC, which is actually practically not possible. So we measure the reference time delay at some very low frequency, let's say 1 millihertz, but you can also do it at 1 microhertz if you want, if that is of course possible in the measurement. Then after that we determine the reference time delay and then determine the time delay at the specified frequency, in this case 4 kilohertz, and then calculate the difference between these two times and then find the percentage in the times so we get the percentage error. Now that's actually what we need to do. So from the Bode plot, this will be clarified shortly how we do that. Now from the Bode plot we see here the phase is minus 35.993 micro degrees at 1 millihertz. So you see that here. It's a very small phase shift. That means actually the following. So looking at it in formula form, you can say now the theta reference is this much degrees at the reference frequency of 1 millihertz. Okay, that's again labeled here. So we need to first convert this degrees in the radians. So that's actually what I do here. So this is the measurement we get from simulation. We divide it by 180 and then times pi, that is the conversion from degrees to radians, that's the formula, and now you get here the radians, which is then 6.28196 times 10 to the power minus 7 radians. Now we also calculate the reference delay time, that is actually using the omega and the theta. The theta we just calculated, that's this, and the reference omega is this 2 pi times this f reference. So again, you can pick another value here, but it's also what you need to do here. So the result will be then very similar to what I have done here. Again, use this value here in the numerator and then 2 pi times 10 to the power minus 3 for 1 millihertz in the denominator. And that will result very close to 100 microseconds, which is of course not a surprise because that's why we design for. So this is the reference time delay. Now going to the simulation result now for the Bode plot for phase versus frequency in the linear scale, and we will see now more details. You see here again the phase. Now you see the phase here in going from 0 all the way up to minus 180 degrees. And this scale here, linear scale, I mean the frequency scale is now plotted in the linear scale. You see here 0, 500, 1 kilo, 1.5 kilo, 2k, so it is not in log scale. That is purposely done to see this relationship, which is indeed linear. So again, our reference delay, which was 100 microseconds, and our time delay error is then calculated using this formula. That means the percentage error in your delay time or time delay is the reference delay minus the delay at that specific frequency, which is in this case 4 kilohertz, divided by the reference delay time. And that times, of course, 100% to get it to the percentages. Now we first need to determine the phase at that 4 kilohertz, which is already here, and then divide that by 2 pi times 4000, and then we are actually almost to the calculation of this time delay error. First this phase, which is actually shown here, and then convert that to the radians, again the similar formula. So you divide by 180 degrees times pi, you get here almost 2.5 radians per radians. That goes in here in this formula, again divided by 2 pi times 4000, so 8000 pi, and you get here 99.2785 microseconds. And this is slightly different than this 100 microseconds, which is of course this error what we actually need to calculate, of course in percentages. So let's do that now using this formula, because now we have all the elements in order to calculate this. So we have here 10 to the power minus 4, which is 10 to the power minus 100 times 10 to the power minus 6. This is actually our reference time delay. We have here value we just calculated or determined from the simulations, and now we have here a percentage error in the time delay of 0.72% almost, which is much smaller than the 10% what we want as maximum. So that's indeed according to specifications. So this is indeed as we wanted. We see in addition the following. I also labeled some extra things here in the plot. You see here at 1 kilohertz phase of minus 36 degrees approximately. And if you now double this frequency, so from 1 kilohertz to 2 kilohertz, you see that the phase is going down also by a factor of 2, which is then here minus 72 by almost here. So which is of course what we want, because we want to have a linear relationship between the frequency and the phase. Now again, if I now make it 3 times larger, then the phase will be also 3 times smaller, and make it 4 times larger, 4 times smaller phase. This is also as we wanted. So again, a linear relationship between the phase and the frequency, which is what we see mostly in Bessel response and not in the Chebyshev response or elliptic response, or even not in the Bode response filter circuits. Alright, it was our example considering the Bessel response delay filter design for this situation, where we have a specification for our time delay error, and the maximum passband attenuation. And we have used the Sallen-Key filter circuit to realize this circuit. If you have any questions, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.